Welcome to section 2.5. As I said earlier, we are skipping 2.4. If you want to open the book and do it yourself, go for it. Ask some questions, do some homework problems, a little bonus learning for you. It would be fun, and I'd be more than willing to talk about 2.4 with you. But for the rest of us, for the rest of you, we're going to skip to 2.5, optimization. So this is a part of the chapter that gets a little sketchy, a little hairy for a couple people. 2.5 and 2.6 can be tricky. So I got an extra video just with an extra example to kind of show you guys more of what's going on here, more options, more things that could happen with the homework problems. But again, it's really important. If you find yourself stuck on these homework problems and just staring at a blank page for an hour, reach out to me on Slack, okay? If you're local, stop by my office. Office hours are best, but if you see my door open, go ahead and knock on the door, maybe introduce yourself, because don't really know many of your faces, right? But yeah, that could be fun. So don't hesitate to reach out. These next two sections are usually a little tricky. And in fact, with that in mind, I believe, if my schedule memory is correct, 2.6 will be the only section for next week. All right, give you a little bit more time to marinate in it. Marinating in mathematics is a very disgusting picture. Anyway, so here's how we find global extrema. First step, find local extrema. Second step, check the ends of domain. So if your domain is closed, then you'll actually just check points. If your domain goes on forever, then you have to check the limits. All right, I know everyone loves limits. It won't pop up very frequently though. And then the last thing is just choose well, your global maximum is whatever the maximum thing we got. Global minimum is the smallest thing we got. All right. So when I talk about endpoints, right, if we're looking at a parabola and this is our domain, then we'll look at the relative maximum here, and then we'll also look at the endpoints here, right? So the local minimum would be y equals 0. But then sometimes we won't have something like that. Sometimes we'll start at 0, but the domain goes off to infinity. In this case, when you find the limit as x goes to infinity, what does this function behave really far to the right? Well, it goes off to positive infinity. So we would say that, okay, there's no global maximum here. But again, our global minimum would be 0. It's kind of what I'm talking about for number 2 and 3. All right. So let's get started. Let's get cracking. All right. Just like a water monster or whatever a kraken is. I don't know. Example 1. Find remember, sometimes we don't say absolute. Sometimes we don't say global. Sometimes we'll just say find the max and the min. That is a weird looking M. Find the max and the min values if they exist. And here our function is going to be f of x equals 12x minus x squared. So if you were really doing section 2.3 and said, man, I really wish we had some extra examples, today is the time for you because we're finding local extrema all day today in this section. Probably should have mentioned that earlier because you may have already done the 2.3 homework. Hopefully you've already done the 2.3 homework. That's usually what I recommend, right? Watch a video, do those homework problems. Watch the next video, do those homework problems. So you don't have to watch 2 hours of math at once. Nobody wants that. Unless you do, in which case, great. So remember, step by step. First step was finding the local extrema. So we need the critical points, right? Critical points are when the first derivative is equal to 0 or is undefined. We'll take the derivative and set it equal to 0. No derivative here. Derivative of 12x is just 12. Derivative of x squared is 2x. Set it equal to 0, and luckily we have a linear equation. We don't have to worry about factoring or anything fancy. We can add 2x to both sides and divide both sides by 2. To get x equals 6 is the x coordinate of our critical point. But again, we have to plug it into the original function to find the y value. You plug it into the original function, you should get 72 minus 36, which is 36. So here, kind of sadly, we only have one critical point. All right. So we can classify this with the first or the second derivative test, but technically we don't really have to since we're checking the endpoints. All right, so that's our step one. Got our critical point. And again, classifying it here is optional. It's good practice, but we're not going to do it here. Next, check the ends of the domain. In this problem, right, didn't specify a domain. So this is just what happens to the function to the right, off to infinity, and to the left, off to negative infinity. And specifically, we know a little bit about this function. This is a downwards parabola. It's a quadratic function. And the x squared term is negative, so we do know it's a downwards facing parabola. All right, so negative x squared term. And it's a parabola that tells us that this function, roughly, is this shape. So to find the limits, right, the limit of this function, as x goes to the right, to positive infinity, that's the edge of our domain to the right. It's going to be negative infinity, right? To the right, it goes down to infinity. Similarly, let's look as x goes to negative infinity. As x goes far off to the left. Again, it's a parabola. It's going the same direction. Going down to negative infinity over here. So our candidates for global extrema are the critical points and our boundaries. So we have three things we need to compare. The critical point, which is at 636, or the edges of the function, which go off to negative infinity. Or we're just going to choose the biggest and the smallest. So we're going to say the global maximum is 36. Sometimes, so again, maximum value is what it's looking for. It's going to be a y value. Sometimes they also ask for the point, like where it occurs. You could say the maximum value is 36 when x is equal to 6. This is the biggest y value for all of these things. For the minimum value, we don't really have a minimum value. Because notice up here, right? To the left and the right, this function's shooting down to negative infinity. It's getting smaller and smaller and smaller. So we say that there is no minimum value because we can always get minimum-er than that. All right. So we'll say no minimum value right here. Now, if the domain was a closed interval, then we would have a minimum value at whichever side of the interval got smaller. But here, our domain is all real numbers, and it's shooting off to negative infinity, so there is no minimum value. We can always get smaller. All right, and that's how you do this problem. And we'll do a lot more similar problems here. They're just going to be in the guise of application problems, but this should get you through the first chunk of problems here. All right.